And dear students, we have already discussed about magnetism. Today we shall discuss about magnetic effects of electric current. What does it mean by magnetic effects of electric current? When a conductor carries current, it is associated with a magnetic field, behaves like a magnet. So, it is associated with a magnetic field, and that is known as magnetic effects of electric current. So, when it is associated conductor, when a conductor behaves like a magnet, it is associated with a magnetic field, and direction of magnetic field is given in some rules. There are rules for the direction of magnetic field. Snow rule. By this rule, you can know what is the direction of magnetic field when a conductor carries current. So, what is Snow rule? Now, imagine a conductor carrying current and a needle magnet is placed below the conductor. If the direction of current is from south pole to north pole, then and the conductor is placed over the needle magnet, then north pole of the needle magnet moves towards the west. So, direction of current is from south to north, conductor is placed over the needle magnet, and therefore, in that case north pole gets deflected towards the west. This is snow rule. Another rule is there, that is your Ampere's swimming rule. Ampere's swimming rule. By this rule, you can also know the direction of magnetic field. Ampere's swimming rule. What does it mean, Ampere's swimming rule? Imagine a man swimming along the direction of current with his face turned towards the needle magnet. If the direction of current is from foot toward the head of the man, then north pole of the needle magnet gets deflected towards the left hand of the swimmer. This is Ampere's swimming rule. Imagine a man swimming along the direction of current with his face turned towards the needle magnet. If the direction of current is from foot toward the head of the man, then north pole of the needle magnet gets deflected towards left hand of the swimmer. This is Ampere's swimming rule. So, by these rules, you can know what is the direction of magnetic field. Then, how much is the magnetic field? You know the direction of magnetic field. A conductor is carrying current, it behaves like a magnet, associated with magnetic field. We can find out the direction of magnetic field. But how much is the magnetic field? What is the intensity of magnetic field? That can be found out. You have to find out that, we apply Biot-Savart law, which is very important from examination point of view. For your examination point of view, Biot-Savart law is very important. You may get long question as well as short question from Biot-Savart law. From this law, you can know what is the strength of magnetic field due to a conductor carrying current. Biot-Savart law. Biot-Savart law, or that is also known as Ampere's theorem. Same thing. In the examination, you may get Biot-Savart law or Ampere's theorem. Normally, long question comes from this Biot-Savart law or Ampere's theorem. So, what is done? Now, we will take a conductor carrying current and find out flux density due to that. How to take that? So, let us. This is a conductor carrying current. Now, here we find out a point P, small element of the conductor. Let us consider a small element of the conductor. We will find out the magnetic flux density at P due to a small element of the conductor. So, let us consider a very small element dl. What is the flux density due to this dl? If you know the flux density due to this dl, you can find out the flux density to the entire coil. So, the point P is situated at a distance r. This angle is theta, this distance is r. So, this entire conductor is behaving like a magnet. So, let us take a small element dl. P is an external point at a distance r from the element. So, what is the flux density at P due to this small element? Let that flux density be dB. Normally, the symbol for flux density B, since the element is small, so flux density is taken as the dB. So, dB depends on what? dB will depend upon what? dB will depend upon current. First, definitely depend upon current. It will definitely depend upon the distance r. At the same time, it will also depend upon how this point is situated with respect to this element. What is the position of the point with respect to this element? So, dB the flux density at P. You know what is the meaning of flux density? Magnetic lines of force per unit area, that is flux density. So, it will depend upon the current strength of current. It will depend upon the length, small length of the conductor. It will depend upon the distance. It will depend upon theta. So, dB first factor, dB according to Bayes-Sabat law, dB direct proportional to I. It must depend upon current. More the current, more will be flux density. So, dB direct proportional to I. Direct proportional to what? The current element, that is dl. Direct proportional to what? Sin theta. Orientation of this distance theta. And how it will depend upon distance? More the distance, less will be flux density. When the distance becomes more, flux density will be less. So, it is inversely proportional to square of the distance. So, dB direct proportional to I, direct proportional to dl, direct proportional to sin theta, inversely proportional to square of the distance. So, these are the factors on which the flux density depends. I, dl, sin theta by what? R square. dB is proportional to I dl sin theta by R square. So, dB is equal to a constant k, I dl sin theta by R square, where k is called proportionality constant. In the examination, we have to write k is proportionality constant. The value of k is different systems of units. In CJC system, value of k is 1, but in MK system, mostly we will deal with MK system. So, the value of k is what? K is equal to mu 0 by 4 pi. I have already told you what is mu 0 in magnetism chapter. Mu 0 is permeability of free space. Value of mu 0 is equal to what? 4 pi into 10 to the power minus 7 Weber by ampere meter. You have to mention this in the examination. K is equal to mu 0 by 4 pi. Mu 0 is 4 pi into 10 to the minus 7 Weber by ampere meter. So, dB is equal to how much? Mu 0 by 4 pi I dl sin theta by R square. This is the expression for flux density due to small element of the conductor according to Bayes-Sabat law. So, in the examination, if it comes state Bayes-Sabat law, you have to write like this. In 7 mark question, 3 marks will be there for Bayes-Sabat law, and for application of Bayes-Sabat law, there will be 4 marks. So, for 3 marks, you write like this. Now, you know that flux density is a vector quantity, magnetic flux density is a vector quantity. Therefore, this flux density can be represented vectorially. How to represent it in vectorial form? So, dB is equal to what? dB vector mu 0 by 4 pi I dl sin theta by R square can be written as what? dl cross R by what? R cube. This is Bayes-Sabat law. Bayes-Sabat law in vector form. In vector form. In the examination, they may ask you short question, write Bayes-Sabat law in vector form. You write like this: dB is equal to mu 0 by 4 pi I dl cross R by R cube. This is Bayes-Sabat law in vector form. So, what is the direction of dB? Direction of dB is what? This is cross product of dl and R. So, the cross product of dl and R is perpendicular plane containing dl and R. So, direction of dB is perpendicular to the plane containing dl and R. So, this is what is your Bayes-Sabat law. If in the examination it is asked what is the Bayes-Sabat law, you write this, there will be 3 marks for this. Now, we will go to applications of Bayes-Sabat law. Applications of Bayes-Sabat law. Applications of Bayes-Sabat law. There are three applications in your syllabus. Applications of Bhatt-Savart law. First application is flux density due to a circular coil carrying current at its center. Second, flux density due to a straight conductor carrying current. Third, flux density on the at a point on the axis of a circular coil carrying current. So, three applications are there in the examination. One application may come as a long question. First application will discuss flux density at the center of a circular coil, carrying current. A very simple application. Flux density at the center of a circular coil carrying current. How to find out that? Let us take a circular coil. This is a circular coil. What is the current flowing through it? Current flowing through the circular coil is I. Similarly, as we have discussed in Bhatt-Savart law, we will take a small element of the conductor, find the flux density to the small element according to Bhatt-Savart law, then find the flux density to the entire coil either by summing up or by integrating. So, for that purpose, let us consider a circular coil carrying current I. A small element is considered dl, radius of the center is O, radius is A. So, current flowing through the coil is I, radius of the coil is A, dl is a small element, O is the center of the coil. We will find out the flux density at the center of the coil. So, let us consider a small element dl. Suppose the flux density due to this element at the center O is dB. According to Bhatt-Savart law, dB is equal to what? Mu 0 by 4 pi I dl sin theta by what? Distance A square. Mu 0 by 4 pi I current is I, element is current dl, angle theta and distance is A. Here radius is equal to distance A. In this case, since a circular, theta is equal to how much? Theta is 90 degree. So, what is dB? dB is equal to what? Mu 0 by 4 pi I dl sin 90 by A square. In this case, theta is 90 degree. So, this becomes equal to what? Mu 0 by 4 pi I dl by A square. This is the flux density due to the small element at the center O. Our aim is to find out flux density to the entire coil. For the entire coil, you can integrate it or you can sum it. So, for the entire coil, flux density B will be what? B will be mu 0 by 4 pi I dl by A square integration. What is the integration? This is a small element. If you integrate it, the total length will be 0 to 2 pi A. 0 to 2 pi A. Mu 0 by 4 pi I dl by A square integration dl. That becomes equal to what? Mu 0 by 4 pi I by A square integration of dl 2 pi A minus 0 L, then 2 pi A minus 0. So, this becomes, this is equal to mu 0 by 4 pi I into 2 pi A by A square. So, this becomes equal to what? Mu 0 I by what? 2 pi for 2, A cancels 2A. Mu 0 I by 2A. So, this is the expression of flux density at the center of a circular coil carrying current. So, we have considered only one turn of the coil. If the coil carries n turns, suppose there are n turns in the coil, in that case for n turns, if the coil carries n turns, B is equal to what? Mu 0 n I by A square 2A. So, remember the formula, for 1 turn or n turns. In the examination, you may get numericals on this. So, for numerical, current will be there, number of turns will be there, value radius will be there, and value of phi 0 you can put and find out the flux density. So, this is your flux density center of a circular coil carrying current. Next application is very important, that comes very often in the examination, that is flux density due to a long straight conductor carrying current, due to a long straight conductor carrying current. This is a very important application, and this comes very often in the examination, flux due to a long straight conductor carrying current. So, let us take a long straight conductor and external point is there, find out the flux density. So, this is a straight conductor, point is P, suppose the distance is A, we will find out the flux density here. Similarly, let us consider a small element dl. We will take a small element, find out the flux density by applying Biot-Savart law, then integrate it to find the flux density due to the entire conductor. So, how to do that? Suppose this distance is r, this angle is theta, this angle is alpha, this is L. This is alpha 1, this is alpha 2. So, these are the notations. Current flowing through the conductor is I. For the small, according to Biot-Savart law, what is the flux density at P? dB will be what? Just apply Biot-Savart law, mu 0 by 4 pi I dl sin theta by r square. Apply put the formula, mu 0 by 4 pi I dl sin theta by r square. In this case, we have a number of variables. In circular coil, we had a single variable, that was the dl only. But in this case, your dl L is a variable, theta is a variable, r is also a variable. So, how to integrate it for all the 3 variables? So, to find out that, let us find out. Let us put the values in for different forms. So, what is this? Tan alpha. What is tan alpha? Look at the diagram. Tan alpha is equal to what? L by A. Tan alpha will now reduce all the 3 variables to a single variable. So, L is equal to what? A tan alpha. We are interested in finding out the dl. What is dl? dl is equal to what? A tan square alpha d alpha. Sorry, A s square alpha d alpha. dl value is known. One value is found. We will find out everything in form of alpha. Then we will integrate. dl is known. Now look at this triangle. Theta plus alpha is 90 degree. So, what is theta? 90 minus alpha. Theta is 90 minus alpha. So, your sin theta will be what? Sin 90 minus alpha, that is cos alpha. Now, we find out the value of sin theta in form of alpha also. So, remaining, what is remaining? Remaining is r. How to find out r? Cos alpha. Cos alpha is A by r. So, r is equal to what? A by cos alpha. So, now we will put the value of dl. dl is s square alpha d alpha, sin theta cos is equal to cos alpha, and r is equal to A by cos alpha. Put all these values here. So, what will be dB? dB will be equal to what? Mu 0 by 4 pi I dl is what? A sec square alpha d alpha. Sin theta, that is your cos alpha, r square a square into cos square alpha. So, these are what? Mu 0 I by 4 pi sec square alpha cos square alpha 1, a cancels a square. So, this is my cos alpha d alpha by a, dB is found out. Now, we have reduced all these three variables to a single variable, and that single variable is what? Single variable is alpha. Now, the extremities of the conductor, that is AB, make angles alpha 1 and alpha 2 at P. So, the flux density at P to the entire conductor can be found out by integrating this expression from alpha 1 to alpha 2. So, flux density at P due to the entire conductor, flux density at P due to the entire conductor is equal to what? B, that is equal to integration mu 0 I by 4 pi a cos alpha d alpha from alpha 1 to alpha 2, from alpha 1 to alpha 2, that is equal to mu 0 I by 4 pi a integration of cos alpha d alpha from what? Alpha 1 to alpha 2. Now, put the integral of cos alpha. What is the integral of cos alpha? Integral of cos alpha is sin alpha. So, put that. So, that becomes equal to what? Mu 0 I by 4 pi a sin alpha from alpha 1 to alpha 2. Mu 0 I by 4 pi a sin alpha from alpha 1 to alpha 2. That is equal to mu 0 I by 4 pi a sin alpha 2 minus sin alpha 1. This is the final expression for flux density due to a straight conductor carrying current. If the conductor is a very long one, in the examination it comes, find out flux density due to a long straight conductor at an external point. So, if the conductor is a very long one, then what will the values of alpha 1 and alpha 2? Imagine, now extend the conductor to a very long distance, conductor is a very long one. So, alpha 2 will be 90 degree, extend this on this side also, alpha 1 will also 90 degree. So, if the conductor is a very long one, if the conductor is a very long one, if the conductor is a very long one, alpha 1 is how much? Minus 90 degree, alpha 2 is plus 90 degree. Long conductor, so alpha will change from minus 90 to plus 90. Put the values, so B is equal to what? B will be equal to how much? Mu 0 I by 4 pi a sin 90 minus sin minus 90, that is equal to what? Mu 0 I by 4 pi a 1 minus 1 2. So, mu 0 I by 2 pi a. So, this is the final expression. If in the examination question comes, what is Biot-Savart law? Find out flux density due to a long straight conductor carrying current. Applying Biot-Savart law, you write like this up to this point. It's all right. Another application is there, flux density at a point on the axis of a circular coil carrying current. That also you can very well find out, because you know the flux density due to a long straight circular coil carrying current at the center. Now, we will find out flux density at a point on the axis of the circular coil. Flux density. These are the applications of Bad-Savart law from magnetic effects of electric current. This Bad-Savart law is the most important from long process. Flux density at a point on the axis of a circular coil carrying current. Circular coil carrying current. At a point on the axis of a circular coil. Three applications are there in your syllabus. So, let us take like this. A circular coil is carrying current. This is the axis of the circular coil O, point is P. We find out what is the flux at the point P due to this long straight conductor P. Suppose the distance is, say for example, distance is A, or you can take distance is x. It is better, take the distance x. Current is, what is the current? Current flowing through this is I. Similarly, let us take a small element of the conductor, find out the flux density due to small element according to Bad-Savart law, then for the entire coil we integrate it. Small element to the conductor dl, radius of the coil is what? Radius is A, this distance is r. This distance is r. This angle is alpha. Current through this. So, flux density at P due to dl, flux density at P due to dl is dB mu 0 by 4 pi I dl sin theta by what? By r square. According to Bad-Savart law, this is the formula. In this case, what is theta? Theta is equal to how much? 90 degree. So, dB is equal to how much? Mu 0 by 4 pi I dl by what? R square. In which direction dB is there? What will be direction of dB? dB will be like this. It will be in this direction. Now, resolve dB into two factors, two components. One component along this, another component along this angle will be alpha. So, this will be dB cos alpha, this will be what? dB sin alpha. dB cos alpha, dB sin alpha. So, dB is resolved into two factors. The vertical component is dB cos alpha, horizontal component is dB sin alpha, dB cos alpha and dB sin alpha. Now, similarly, as dl is here in the upper part, similarly dl will be there in the lower part. Every element will have a diametrically opposite element. So, also find out the flux due to that element. This is also dB, and direction of this dB is like this dB. You can resolve this dB into two components. In this direction dB cos alpha, in this direction dB sin alpha. This angle is also alpha, this is also alpha. dB sin alpha. Vertical dB cos alpha, horizontal component dB sin alpha. For this component, this part also dB cos alpha and dB sin alpha. When you look at the diagram, you see dB cos alpha, the upper element is just opposite to dB cos alpha, the lower element. So, both the components will mutually cancel. So, when the entire coil is considered, the flux flux density at P due to the entire coil, flux density at P due to the entire coil is equal to B, that is equal to how much? Summation of all dB sin alpha, summation of all dB sin alpha. Now, you put the value of dB and put the value of sin alpha, you find out flux density at center of a circular coil carrying current. How? What is dB? We have already found out. dB is equal to mu 0 by 4 pi I dl sin I dl by r square, that is equal to summation mu 0 by 4 pi I dl by what? I dl by r square into sin alpha. From the diagram, look at sin alpha. What is the value of sin alpha? A by r, A by r. It's all right. Mu 0 by 4 pi I dl. So, this is equal to mu 0 by 4 pi is a constant, I is a constant. Now, see summation mu 0 by 4 pi I dl A by r cube. So, that is equal to what? Mu 0 by 4 pi summation I dl A by r cube. What is r? X square plus a square, x square plus a square to the power 3 by 2. Now, what to sum up here? All are constant. d mu 0 by 4 pi is a constant, I is a constant, a is a constant, x is also distant, that is also a constant. The only variable is dl. So, that is equal to what? Mu 0 by 4 pi I a by x square plus a square to the power 3 by 2 into summation of dl, that is equal to how much? Mu 0 by 4 pi I a by x square plus a square to the power 3 by 2 summation of dl 2 pi a. So, that becomes how much? Mu 0 by 4 pi, you can keep it the constant as such, 2 pi a square I by x square plus a square to the power 3 by 2. So, this is the expression of flux due at a point of the axis of a circular coil carrying current. For n turns, if the coil carries n turns, suppose the coil carries n turns, for n turns B is equal to what? Mu 0 by 4 pi 2 pi a square n I by x square plus a square to the power 3 by 2 for n turns. From this also you find out what is the flux density at the center of a circular coil, because the center is also a point on the axis. For the center, which distance is 0? X is equal to 0. Put it here, x is equal to 0. So, this becomes mu 0 by 4 pi 2 pi a square n I by what? A cube, that is equal to mu 0 by 2 n I by a, as we have already found out in case of a circular coil. Same formula now we have getting. So, these are all three applications of Bart's law. So, if you are getting a long question from this chapter, it is very important and you can very well answer the questions. Next is force exerted on a charge moving in a magnetic field. Force exerted on a charge, force exerted on a charge moving in a magnetic field. Force exerted on a charge moving in a magnetic field. force exerted on a charge moving in a magnetic field. Suppose there is a magnetic field in which a charge is moving. So, what is the force exerted? So, force exerted on a charge moving in a magnetic field will depend upon the factors. What are the factors? How much charge is moving, with what velocity is moving, and what is the strength of the magnetic field. So, that force is given by what? F is equal to Q V cross B. I have already told you what are the factors on which force will depend. Force will depend upon the first, how much charge is moving, with what velocity charge is moving, and what is the strength of the magnetic field, that is magnetic flux density. F is equal to Q V cross B. That is equal to what? Q V B sin theta. You know cross product of two vector Q V B sin theta into n cap. What is n cap? Where n cap is unit vector perpendicular to V and B. N cap is unit vector perpendicular to V and B. So, what is the direction of force exerted in the conductor? The direction of force is perpendicular to the plane containing V and B. Plane containing V and B. What is the maximum force? When the force will be maximum and when no force will exert it? If V is equal to 0, suppose the charge is not moving. If the charge is at rest, F is equal to 0. So, there is no force exerted in a conductor if it is at rest in a magnetic field. F is equal to 0. If the charge is moving parallel to the magnetic field, suppose charge is moving parallel to the magnetic field or in the direction of magnetic field, charge is moving parallel to the magnetic field or in the direction of magnetic field, in that case theta is equal to 0. So, F will be what? F will be 0. So, no force is exerted in charge move either at rest or moving parallel to the magnetic field. So, if theta is 90 degree, that means the charge moving perpendicular to the magnetic field, F is what? QVB maximum. So, maximum force is exerted in a charge moving perpendicular to the magnetic field. You can get short questions from this, 1 mark question, 2 mark question, also numericals. Numericals, say electron is moving in a magnetic field, strength of the magnetic field will be given to you, and velocity will be given, what is the force exerted on it. So, from this you can find out the unit of magnetic flux density. Unit of magnetic flux density from this expression, unit of B, Let us first discuss MKS system. Unit of B, flux density. F is equal to what? QVB sin theta. This is the formula. MKS system. If Q is measured in Q is measured in coulomb. Q is measured in coulomb, charge is measured in coulomb. V in meters per second, velocity in meters per second. F in Newton, MKS system, Newton. Then B will be measured in what? B will be measured in Tesla. Then B will be measured in Tesla. Measured in Tesla. So, MKS system, in MKS system, the unit of magnetic flux is Tesla. So, what is Tesla? B is equal to what? Fy QV sin theta, that is Newton by Coulomb into meter by second. Meter by second. Velocity is meter by second. Newton into second by Coulomb into meter. That is your Tesla. Tesla. F is Newton, Q in Coulomb, V in meter per second, you need Tesla. How to define 1 Tesla? How to define 1 Tesla? 1 Tesla will be that if charge is 1 Coulomb, velocity is 1 meter per second and force is 1 Newton, then in that case strength of the magnetic field will be 1 Tesla. In CGS electromagnetic unit, CGS electromagnetic unit, B is equal to what? Same formula you can put, F by QV sin theta. Put the unit of F dyne, Q EMU of charge, EMU of charge, V centimeter by second, and sin theta has no unit. So that becomes what? Dyne into second by EMU of charge into centimeter. This is known as what? Gauss. So unit of magnetic flux density in the CGS electromagnetic unit is Gauss. In MK system it is Tesla, in CGS system it is Gauss. Now you can correlate, as you have already correlating so many units from CGS system to MK system. Similarly, you can have a correlation between Tesla and Gauss. Relation between Tesla, these are very important. Relation between Tesla and Gauss. Tesla and Gauss. How to correlate Tesla and Gauss? 1 Tesla is equal to 1 Newton into second by Coulomb into meter. Now we will put it, convert it to Gauss. So let us place in place of Newton, let us take how much? 10 to the power 5 dynes. 1 Newton is 10 to the power 5 dynes. Second remains as second. 1 Coulomb. 1 Coulomb is how much? 1 Coulomb is how much? 1 by 10 EMU of charge. 1 Coulomb is 1 by 10 EMU of charge. Meter 100 centimeter. 10 by 5 dynes into second, 1 by 10 EMU of charge into 100 centimeter. So look at the figures. How much you get? This becomes 10 to the power 4 dyne into second by EMU of charge into centimeter. What is this? Dyne into second by EMU of charge into centimeter, that is 10 to the power 4 Gauss. So 1 Tesla is how much? 10 to the power 4 Gauss. 1 Tesla is 10 to the power 4 Gauss. Dimension of flux density. Dimension of flux density. Dimension of flux density. These are very important from examination point of view. In the examination, you will be asked to find out dimension of flux density or unit of flux density. If in 1 mark question it may come 2 marks, etc. So from this formula I can find out QVB sin theta, dimension of V. F is equal to QVB sin theta. So how to find out the dimension of V? V dimension is equal to F by QV sin theta. So to find out the dimension of V, let us put the dimension of F, dimension of Q, dimension of V and dimension of sin theta. As you know, what is the dimension of force? mL t to the power minus 2 force. Charge, current into time, AT, velocity, L t to the power minus 1. Sin theta has no dimension. ml to the minus 2 at charge is current on time at into velocity is L to the minus 1 t to the minus 1 cancels, L cancels. So, remains what? M a to the power minus 1 t to the power minus 2 m a to the power minus 1 t to the power minus 2. This is dimension of flux density. Now, we have discussed the force acting on a charge moving in a magnetic field. When a current flows through a conductor, charges are moving, and if the conductor is placed in the magnetic field, it will also experience force, because the charge is experiencing force. So, force acting on a conductor, force acting on a conductor carrying current in a magnetic field, in a magnetic field, in a magnetic field, force acting on a conductor carrying current in a magnetic field. How to find out the force acting on a conductor carrying current placed in magnetic field? From the previous formula, you can find out. This is given by what formula? I L cross B, because this force will depend upon how much current is flowing, what is the length of the conductor, and what is the magnetic flux density. So, the formula is what? F is equal to I L cross B, that is equal to what? I L B sin theta into n cap. This is the expression of force exerted in a conductor carrying current placed in a magnetic field. If theta is 0 degree, no force is exerted, that is, the conductor is along the direction of magnetic field, no force is exerted. If theta is 0, F is equal to 0. So, no force is exerted in a conductor carrying current placed in a magnetic field. If theta is 90, F is equal to how much? ILB, that is maximum. So, maximum force is exerted on a conductor carrying current if it is perpendicular to the magnetic field. This force is, the direction of this force is given by a very important rule, that is Fleming's left hand rule. Fleming's left hand rule. Fleming's left hand rule. This is very important. It very often comes in the examination. Fleming's left hand rule. So, this rule gives you the direction of force exerted in a conductor carrying current. So, that is like the statement is like this: stretch the three fingers of your left hand, the forefinger, the middle finger, and the thumb in such a way that they are mutually perpendicular to each other. Stretch the forefinger, middle finger, and thumb of the left hand in such a manner that they are mutually perpendicular to each other. The forefinger represents the direction of magnetic field, direction of B. The middle finger gives the direction of current, current is flowing. Then the force will exerted, direction of force will be given by thumb of the thumb. So, remember the rule: stretch the three fingers, that is forefinger, middle finger, and thumb of the left hand in such a manner that they are mutually perpendicular to each other. If the forefinger represents the direction of magnetic field, in the middle finger represents the direction of current, then thumb represents the direction of force exerted. So, this rule is the working principle when electrical current, electrical energy is converted to mechanical energy. That is working of principle of a motor. That is when electrical energy, suppose you apply current to a fan is moving, this rule is applied there. Electrical energy is converted to mechanical energy. Fleming's left hand rule will be applied when electrical energy is converted to mechanical energy. So, direction of force is given. Similarly, in alternating current chapter, we will read Fleming's right hand rule. There mechanical energy will be converted to electrical energy. From mechanical energy, you will get electrical energy. You will move a conductor in a magnetic field, get electric current. Here you are applying current to a conductor and getting the force, so the conductor is moving. So, Fleming's left hand rule. This is very important. Statement is important. means left. Next is Lorentz force. Lorentz force. This Lorentz force is also important from examination point of view. For 2 marks question or 3 marks question, Lorentz force. What is a Lorentz? What is Lorentz force? When a charged particle is subjected to electric field and magnetic field simultaneously, it experiences force due to electric field and also force due to magnetic field. The resultant force is called Lorentz force. So, you can remember it. When a charged particle is subjected to electric field and magnetic field simultaneously, it experiences force due to electric field as well as force due to magnetic field. The resultant force is called Lorentz force. When a charged particle, writing this, when a charged particle is subjected, when a charged particle is subjected to electric field and magnetic field, simultaneously means at the same time. When charged particle is subjected to electric field and magnetic field simultaneously, it experiences force due to electric field and also due to magnetic field. The resultant force is called Lorentz force. This Lorentz force comes in the examination carrying either 2 marks or 3 marks. The resultant force is called Lorentz force. What is the expression for force Lorentz force? F is equal to QE plus Q V cross B. Q V cross B. That is your Fe plus what? Fm. Fe force due to electric field, Fm force due to magnetic field. Charged particle is Q, electric field strength is E, magnetic flux density is B. So, what is the force exerted? QE plus QV cross B, Fe plus Fm. Fe force due to electric field, force due to electric field, force due to electric field. Fm force due to, that is equal to QE. QE force due to electric field, QE. Q is the charge and E is the electric field strength. Fm force due to magnetic field, force due to magnetic field, that is equal to what? As we have already discussed, QV cross B. B is velocity of the charge and B is magnetic flux density. QV cross B, force due to electric field QE, force due to magnetic field QV cross B, charge is Q, V is velocity of the charge, B is magnetic flux density, E is electric flux density. So, this is your Lorentz force. Lorentz force comes in the examination. You write like this: when a charged particle is subjected to electric field and magnetic field simultaneously, it experiences force due to electric field and it experiences force due to magnetic field. The resultant force is called Lorentz force. Then what is the work done by Lorentz force? Suppose in the examination question comes, what is the work done by Lorentz force? How much work is done by Lorentz force? Total force exerted is how much? F is equal to Fe plus Fm, QE plus QV cross B. So, when in the question of work done by Lorentz force, we have to find out what is the work done due to electric field, what is the work done due to magnetic field. Work done due to electric field, how much work done due to electric field? Force due to displacement. What is the force due to magnetic field? you see force due to magnetic V cross B. What is the direction of this force? Direction of this force is perpendicular to V and perpendicular to B. And when question of work done will come, then it will be dot product of this force and displacement work done. So, in that case, this factor direction of force and direction of displacement will be perpendicular to each other. Direction of force and direction of displacement will be perpendicular to each other. So, no work will be done by force due to magnetic field, only work will be done due to electric field. For work done by Lorentz force, for work done by Lorentz force, no work will be done by force due to magnetic field. Force due to magnetic field. Work will be done only force due to electric field. Work will be done due to force exerted by electric field. So, this is about your Lorentz force. If there are two conductors, suppose there are two conductors carrying current, this will have a magnetic field, that conductor will have a magnetic field. If current flows in the same direction, what will happen? Normally the students are confused. They will if the current is flowing in the same direction, they will write that they will repel each other. No, when current flows in the same direction, the conductors will attract each other. When current flows in opposite direction, the conductors will remember that. That is a very important short question in examination. When current, therefore there are two conductors are there, parallel conductors are there. If current is flowing in the same direction, they will attract each other, and current flows in opposite direction, they will repel each other. This is very important, remember this. So, these are some discussions on magnetic effects of electric current. In the next class, we shall discuss about the galvanometer, ammeter, voltmeter, etc. So, these are equipments where magnetic effects of electric current are applied, because in that case we apply this principle to construct a galvanometer. As you know, galvanometer is an instrument by which electric current can be measured, and that can be converted to an ammeter to measure current, that can be converted to a voltmeter measuring potential. In next class we shall discuss that.